Good morning. My name is William Billini.
Xavier, Bercy.
And I'm Ricardo, Charlestin.
And we're Team L, and our project is a digital photolithography system. So our problem statement is to innovate the process of creating printing screens. As pictured here on the right, this is the process of printing images onto t-shirts. So we want to innovate the process of creating the screen itself. Our objective to get that done is by designing a digital photolithography system with motion control and machine vision. Our motivation for that is to eliminate consumables. Pictured at the very top is a what's called a film positive, which is printed on polyester film. Other motivations are to boost productivity and to improve image quality. So essentially, our goals are to make the process of creating printing screens better, faster, and cheaper. So what is photolithography? Photolithography is the process of transferring patterns via optical methods onto a photoresistive material. The spectral range that we're going to be working in is within 350 to 420 nanometers. Pictured here is an application of photolithography using digital micromirror devices by Texas Instruments. On the right, there is an optical light that is illuminated onto the chip, which has an array of microscopic mirrors, and it then reflects a pattern onto the photoresistive material. This illustration shows how printed circuit boards are manufactured now. So we're going to use this same application to emit patterns onto screen printing frames. So essentially in business you have two challenges when delivering service. Usually you're constrained to two, either better service, faster service, or cheaper service. So our goals is to deliver all three. We're going to deliver that by improving the image quality that is projected onto screen printing frames. We're going to make the process of creating screen printing frames faster by reducing the amount of steps required to expose the screen. And we're going to make it cheaper because we're eliminating the need for consumables. So the first project deliverable, how are we going to improve the image quality? That is going to be through the optic system by collimating the light. And what collimate means is to make rays of light parallel. So we have two examples of what we want to deliver to the customer. On the left is a poor quality exposure. Notice the curved edges. That's caused by light diffraction from the conventional method. On the right, we have an example of good quality. Notice the sharper edges. Both of these pictures are magnified 100 times. So a standard that we're going to use to ensure that we deliver a very good resolution is the military standard 150A. This pattern is used to calibrate optical systems like guidance tracking systems used to drop bombs. So our plan to prove that this is going to be it's going to make the process of creating printing screens faster. We're going to create a computer simulation which compares the current state process against the future state process. What you see here is a flow chart. The conventional process requires 13 steps. We're going to reduce that down to 6 steps. So our computer simulation is going to output the savings in time. And why is it going to make the process of creating printing screens cheaper? We're going to create an economic analysis where we're going to calculate the savings from consumables, which are shown here on 3 standard printers. What's happening here is that they're printing onto polyester film, and then that polyester film has to be cut by hand, so it is then adhered to the screen printing frame before it is exposed. On top of the savings from consumables, we're going to take the time, which we've calculated from the previous analysis, and come up with an economic analysis to determine a return on investment for, let's say, $300,000. Well, let's say the system were to cost $300,000.
All right. The conceptual design for our proposed system will be made of two major components: a light engine, a motion control, and a machine vision. All those three will be working together in a closed-loop design as an automated industrial system. The light engine contains a digital micromirror device similar to a conventional video projector that will project the image of the pattern of the images onto a photoresistive material with UV radiation. And it also contains an optical system which is optimized with LED technology to provide perfect light distribution, and uniform in color. And as well, the light source that will be used will be salvaged from a Panasonic PT-D4000U, which is one of the best out there suitable for our project. And it also contains a heat exchanger and thermal sensors on board, simply for full or faster thermal evaluation of the system itself. For the motion control, we will be using 3-stepper motors, most likely Nemo type, just to allow control in 3 different axes. The light engine will be mounted on a belt-driven linear actuator, and it will be fixed onto an axis parallel to the floor, so that the motion control system itself was essentially synchronized with the light engine and the motion of the screen printing, so that the image can be patterned on the frame in a serpentine pattern. And next we have our machine vision, which will be like a video camera that will be mounted on top of the conveyor belt. The camera will be able to measure the dimensions and the orientation of the screen printing frame, so that the light engine will be able to use those coordinates to apply the image onto the screen printing frames. And here a proof of concept of a poster note with MATLAB code that we execute, and we were able to get that result, which shows that we will be able to code the camera to measure the dimensions of the screen printing itself.
So here's our project timeline. The way that we have it organized is that the 3 separate components are to be designed and fabricated in parallel. We have the light engine, the motion control, the machine vision, all to be done by the beginning of March. That will allow us to assemble the entire system, calibrate, and do some final testing between January and February. The goal is to complete the system by February to allow us to work on the report and also rehearse for the final presentation during the month of March. So, global perspective elements, we're going to be focusing on 3 international safety standards, since it is an industrial automated system, and the operator is going to be in close contact with it, so we need to follow safety standards. We are going to create a multilingual manual, and we also have to observe electrical compatibility in other countries. So, in conclusion, this is a multidisciplinary project encompassing mechanical engineering, electrical and computer engineering, and industrial engineering. Pictured up top is the actual driver board that we're going to be using for our DND. That has an onboard FPGA, a field programmable gate array, which is going to require programming of in the VHDL language. So that's something new that we're learning. As far as industrial engineering, we have to create an industrial simulation. So that's also something new that we have to learn for this project. And for the mechanical engineering component, the linear actuators, we have to design those parts and build them and make sure that they withstand the forces that we're going to put on the system. So in summary, our objective is to create a digital photolithography system in order to innovate the process of creating printing screens. Our light engine will utilize a DMD, a digital micromirror device, and we're going to integrate machine vision and motion control. Future work for this technology. There exists a market demand for desktop systems similar to desktop 3D printers. This would be a more affordable system for smaller scale screen printing shops. For higher end systems, there exists the opportunity to schedule jobs directly from an ERP, an enterprise resource planner. There needs to be improvements in the quality of the LED light source to ensure that the intensity of the light reaches the substrate. And further improvements for the optical system would allow narrower line widths than 40 micrometers. Here's our poster. Pictured with the DMD assembly and all our information. So, any questions?
Let's see a budget.
A budget? Well, we have so far accumulated about $10,000 worth of equipment for free. We've only spent $150. Mainly for the DND chip, which is used, and also the DND driver board, which we also found on eBay. Do you mean a budget for this project, or a budget for, let's say, a system that would be sold on market?
Well, you were talking about a desktop level as being the ultimate end item that you would ultimately come up with besides your prototype that you're building. Mm-hmm. So it seems like it would be advantageous to know what that budget is. I have no idea whether that a desktop is a $50,000 item or a $3,000 item.
Well, we haven't determined that yet. What we meant from the very last slide, from our conclusion, is future work improvements beyond our project. So that when future researchers are reading our report, these are things that they can work on. But for our project, we're limiting the scope to a full-scale system with the motion control, the machine vision, and the light engine.
Okay, I'm a silk screener and I'm looking to buy one of these things. And I don't think that t-shirt silk screeners have a huge budget for this. So I don't really know, but I've been in some silk screen places, right, and they're not real fancy, and they don't have a lot of fancy equipment in them for the most part.
Yes, that is true. Basically, what has been done, a economic analysis from a place that I used to work at. I used to work at a screen printing shop. And what we've determined is that that company themselves, they're a what's known as a top 40 supplier in the screen printing industry. They spend $100,000 a year on consumables. And then on top of that, there's $150,000 spent on labor related to creating the masks. So right there in 1 year, they're spending $250,000. I mentioned $300,000 earlier because that would still allow them to buy the system and have a return on investment of less than 2 years.
So your budget then is 300,000?
Yes.
Okay.
I see what you're saying. Okay.
That's a lot of words to get there.
Now, on your global slide, you sort of mentioned about the safety standards, etc. Could you talk more about the standards that you are going to use in your project?
That is still to be determined, but we do know that we have to look at UL standards in order to make the system safe to work here in the United States. We also have to look at CE standards to see how they would be safe in Europe. So that's what we know for now.
What about the other standards? Did you look at any other standards? Because you didn't really talk about standards.
Well, we do know that we have to look at NEMA standards. One for the motor. There is going to be an electrical panel. So it has to be, we don't have that yet. But we have an idea of what we need to look for.
Now, this question is about rules. And maybe Xavier, right? Is that your name? Xavier? Yes. Maybe you can answer this question. Could you talk a little bit more about the roles, what your role is, and the roles of your teammates? Yes.
My role is to basically put, I'm the solid design engineer. Solid design, so basically I'll design the project, how the project is going to look like. And my teammate here, he's basically the writer writing part of the team to see how the format of our project, how it's going to look like. And basically he's the manager, the main person of the team. Yeah.
Organize everything.
Ricardo's our people person. He keeps us in check. So
UV curable photoresist is what you're using?
yes, sir.
How expensive is that?
It's not very expensive. We're going to utilize. Well, that's a good question. We don't have the price for that.
You're going to find that's very expensive.
Okay.
So when you do your analysis, I'd start there.
Well, the analysis, it's not going to change the required photoresist. That's why it doesn't, we haven't even considered that.
But when you balance it compared to conventional photo approaches that you can make in the screens, you got to look at, is that cost going to make you cost prohibitive?
The goal is so that the company that purchases it, they're not going to have to change the photoresist that they're already using.
So the current photoresist that they currently use in their systems will work with this system?
That is correct.
Okay. Sensor. How big is the effective area on the sensor?
The sensor on the digital micromirror device?
Correct.
It has an array of 1024 by 768 pixels. Each one measures approximately 14 micrometers. That is about an inch wide by just under an inch tall.
Are you going to be flashing and moving? Are you going to be using a video type approach? How are you going to ensure the accuracy of one image to the next image?
What do you mean, the image actually projected?
Correct.
Or being...
You're basically putting a light source that's got to match to the next light source, that's going to match the next light source to make this continuous output on your screen. How are you going to execute that?
Well, the light engine is self-contained, so it has the light source in it. The light is illuminated onto the DMD, and then the images that we want to project onto these screens, they're going to be uploaded as bitmap images to the onboard memory. then code is going to be executed so that it refreshes the image, I believe right now at the rate of 32,000 times per second. So it's going to work.
Okay, but again, your sensor's moving.
Yes, it is.
So you got to connect each of these sets to each other
No,
in order
there's
to
only
create the
one.
whole event.
Yeah, there's only one, okay? And so before we upload the image, we're going to create the program to basically create the path for the motion control system. And the images are going to be modified in such a way so that they synchronize as they're moving. So basically, that's how we're going to do that. And we're going to achieve that by creating a series of frames of images as it's moving along. So for every increment of motion, a new frame is going to be loaded.
The question, your logo and also fencing pattern.
I'm sorry?
The logo and also fencing pattern. I mean, the image. It's not only one time. We'll keep repeating it. So
Right.
it's like an already get.
So the image width that's actually going to arrive at the photoresist, it's going to be magnified by 1.4 approximately. So the image width on the screen is going to be just under 1.5 inches by 1 inch. So we have an entire screen to expose. How's that going to happen? The light engine is going to be mounted on a horizontal axis and it will scan across. The conveyor belt will move the screen printing frame in the perpendicular axis. So we're going to have